Gettysburg Seminary presents the Seminary Explores podcast. Conversations on faith, art, people, politics, theology, life, and more, with voices from around the corner and around the globe.
Welcome, everyone. My name is Kristen Largent, and I'm here with the Seminary Explores podcast, and I'm delighted to welcome our guest, Dr. Craig Foltz. Dr. Foltz is an adjunct lab instructor in the physics department, having joined the staff in 2015 following a retirement from a 4-decade-long career in research astrophysics, and also he served as program manager at several university and research centers, and we've been having some conversation before we went live, and he's had really quite a fascinating career. So, Craig, it's really great to have you with us.
It's great to be here, Kristen. Thank you very much.
So we're continuing. I had said that we have been interviewing some scientists from the college. You all have been great down there to come up and share your time and expertise with us. In light of the fact that we did receive an AAAS grant to talk about science in the seminaries and why science might matter to people of faith. And so it's great to have you. And I thought we'd start by just having you say a little bit about how you got into physics. Sure. And a little bit what you do and
Sure. I grew up in the 60s, went to college in the 70s, and I don't know why I studied physics. I know why I studied astrophysics.
Okay.
And I was at Dartmouth College in New Hampshire, and this was an era when we were first starting to talk about black holes.
Oh, yeah.
And obviously none had been discovered. They were theoretical arguments that they should exist and so on, and if they did exist, what could they do? And so there was lots of discussion about that. And also there was a lot of curiosity about very, very luminous objects in the universe called quasars, or quasi-stellar objects, which I think are still the most luminous. They put out the most energy of anything in the universe, and actually it turns out they're very large black holes.
And I'm going to just have you stop and say, just to remind all of us, what a black hole is and what a quasar is.
Okay, a black hole is a collapsed object. We all know about gravity. Gravity means that all matter attracts all other matter, for the most part, as long as it's not charged or anything. And so if you take an object like the sun, the mutual gravity of all the material in the sun tries to make it collapse. And that is offset in the sun by the fact that there are nuclear reactions going on at its center, which increase the temperature and the pressure, and that supports the sun against collapse. Okay. So it's in what's called equilibrium.
Is that what's going on for the Earth also?
The Earth has structural strength.
Okay.
This would be, I'm talking about something gaseous.
Oh, got it. Okay, yep.
Like a star.
Okay.
If those nuclear processes at the core of the sun stopped, the sun would collapse, and it would continue to collapse until there was something that would stop its collapse.
Does that happen quickly or over?
No, it's over some period of tens of millions of years.
Okay.
You got no problem.
Okay. I'm good.
We got 4.5 billion years.
Okay.
And the sun will, actually what will happen is the sun will get very, very large. It encompass the Earth, will burn up, and then eventually the sun will collapse into this thing called a white dwarf, which is an object about the size of the Earth with the mass of the sun.
Wow.
Extremely dense material.
Okay.
And basically, it's supported because you can't push electrons too close together.
Okay.
It's called electron degenerate matter.
Okay.
And so that stops it. It will not collapse any further. If you took a star that was several times bigger, and there's another alternative sort of in-between state called a neutron star, but if you take a star that's, say, 2.5, 3 solar masses to collapse, nothing can stop the collapse.
What force overcomes the repelling of the electrons? And just the gravity is so strong.
The gravity is trying to make it collapse. The fact that you can't push the electrons any closer together is opposing that collapse.
Okay.
So it'll have a spherical structure.
Okay.
And it'll just sit there and cool off and turn into a...
But in these really big stars, the gravity is strong enough
strong enough that it actually forces the electrons into the nuclei. In the end, it produces something that is so small and has such overwhelming gravity that no light can escape from it.
Wow.
Okay, so and light is affected by gravity.
Okay.
It's weak. Gravity is the weakest of the fundamental forces. So in a situation like that, if light can't get out, the escape velocity is faster than the speed of light. You can't go faster than the speed of light. And with I'm not going to talk about quantum mechanics, but essentially that material that has collapsed has sort of pinched itself out of the universe, and all that's left is this mass.
Okay.
There's no light escaping from it.
Okay.
Things can fall into it. It can accrete matter. Gas can flow into it.
Okay.
Okay, now we know these things exist. We know there's one at the center of our galaxy. We really do know this, although, we have very exquisite data that show that there is a very large collapsed object at the center of our galaxy. It's about 3 million solar masses.
Wow.
And it has stars that orbit around it, and we watch these stars orbit around this thing that is producing no light.
Okay.
So
we know it's something that's got a gravitational force.
It has that kind of mass.
Okay.
Okay. And we believe that there's probably such a creature's not a good word, such a structure, a black hole, a large black hole, at the center of every large galaxy.
Wow.
And in many cases, for very large black holes that are accreting matter, as the matter falls into the black hole, it heats up dramatically. It emits a lot of light. It's very luminous.
Okay.
Now, the light is not coming from inside the black hole. It's coming from material that's falling onto it.
Wow.
And these were first sort of first understood in the 1960s. I remember this. I remember Time magazine had the picture of Martin Schmidt, who was an astronomer who's only recently died. Recently in sort of my terms, maybe 15 years ago.
Just a moment ago. Yes, fair enough.
But he was their cover picture because he understood that these things that looked like stars, they were a little fuzzy, so they were called quasi-stellar.
Oh, okay.
Were actually objects at extraordinarily large distances, further away than anybody had ever seen anything before. Now, by what we know now, it was a pittance. It was next door.
Yeah.
But because we could see them, and because they were so far away, they had to be producing enormous amounts of energy.
Okay.
And so that's what I studied in my research career, which is, I'll say, is we put it into sort of temporary suspension for a while. I don't.
What does that mean?
I don't do much research anymore.
Okay.
In fact, for the last 12 years or so, I worked in support.
Okay.
I worked for the National Science Foundation, which is an independent agency of the federal government.
Okay.
An independent agency means we did not work under a cabinet member. So NASA isn't. That's a federal term.
Okay. Well, yeah.
Yeah.
Okay.
There are independent agencies, and then they're not. NSF has about a 7.2. I may be living in the past here. $1 billion a year budget, and it's charged with supporting science, technology, education.
Wow. But all branches of science, right?
Not except for health sciences.
Oh, okay.
NIH does.
Oh, sure. Yeah. Okay.
So I worked in the Directorate of Math and Physical Sciences, which was physics, astronomy, chemistry, math, material science.
Okay.
And then there was a directorate for biology and so on.
Okay.
I worked in a division of astronomical sciences, and we supported small awards to individuals, small teams. These might be awards of a few $100,000, maybe up to $500,000 or so for a 3 or 4 year award, and small groups. And we also supported very large multi-user observatories that were available to anybody who wanted to use them, as long as their proposal withstood merit review.
Yeah.
And so I worked in support of that, mostly overseeing very large telescope projects.
Okay.
Including a brand new solar telescope that's being built on Maui, on top of Haleakala.
Right.
And a very large cosmic camera called the Large Synoptic Survey Telescope, which in 10 years we'll all know about, because it'll be it's the coolest project that I've ever been involved with, which is being built in Chile.
Wow. Are all of these projects international kinds of projects? I mean, do you all play well with others across national?
We try.
Okay.
We try. And we've always been, I think I can stand a very, I puff up my chest and say we have always accepted proposals independent from country of origin.
Oh, that's great.
Independent of citizenship.
That's great. That's great.
And that came at some expense. There are other national facilities built by other nations where U.S. astronomers are not welcome.
Okay.
This is changing.
Okay. Who turns out great astrophysicists?
We still do the best.
Do we?
We
do.
Okay. We do. We know how to train researchers.
Okay.
We know how to build collaborations.
Okay.
And we know how to build wonderful, wonderful facilities that can be run, well, I'm going to say for reasonable costs.
Okay.
But those reasonable costs are tens of millions of dollars.
Yeah, of course.
So, astronomy is expensive. It's not expensive like very high energy physics, for example.
Okay.
Our facilities don't touch things like the Large Hadron
Collider. Okay.
Yeah. But, we are now entering an era where the new generation of telescopes are approaching, let's say, 300 million to $1 billion. That's a lot of money. And at that level, even from the feds, it's very difficult to raise that kind of money inside. Yeah. And you are encouraged, it's a little schizophrenic, where you're encouraged to find international collaboration.
Okay.
But then the complexity of the management
I can imagine.
becomes extremely expensive.
Yeah.
And so one has to sort of defend and understand. And when somebody put it once, we recently completed a large radio telescope array called ALMA, and it's at 16,000 feet in the Atacama Desert in Chile.
Okay.
It's an array of radio telescopes. It's fabulous. It's the kind of thing you say, this gives me faith in our species. That we would do this.
That we could do something
that we would even think to do this. Right?
Okay.
It really gives me chills. But it was a joint project. It's about it's about 40% U.S. money, an awful lot of U.S. expertise. 40% European Southern Observatory, and then the Japanese are in, the Canadians are in, Taiwan is in.
Okay.
And as the project manager once said, talking about the interaction between the countries, said, even if you're a minor player, if you're contributing $250 million, you cannot afford to lose any arguments.
Huh.
So management got very complex.
Yeah,
oversight gets very complex.
Sure.
And there are cultural differences.
Yeah, I bet.
And so that's always a challenge, and it's not necessarily a challenge that scientists are trained to deal with.
Well, I want to come back to the telescopes, but first I want to ask you what the difference is between an astrophysicist and an astronomer.
There's no difference.
Oh, okay.
There's really no difference. There was there was a time when everybody was called an astronomer.
Okay.
And there were astronomers who did things that were very sort of foundational, looking at the motions of stars in the sky.
Yeah.
That's very important. It turns out it's a lot of our understanding of the universe depends on our understanding of how the galaxy works and how how stars pulsate and so on, and what their masses are. And these were very sort of standard observations. There wasn't a lot of physics involved.
Yeah.
You wrote them up.
Right.
And then starting with in the 40s or so, when we started to understand what makes stars work, which we didn't. Remember, this is all new.
Yeah.
We didn't know about fusion.
Yeah, sure.
Relativity, early 20th century.
Yeah.
But it wasn't 100 years ago that we didn't know what these fuzzy patches of the sky were that were outside of the Milky Way. Away from the sky, extragalactic, out of the Milky Way. Now we interpret that as way out, but this was just in the sky. And it was Hubble and others who said, "Oh, these are other systems like the Milky Way." That was less than 100 years ago, right? So now amazing. We know there's hundreds of billions of other galaxies.
Yeah.
And we see them way back in time, and we're trying to see them be created, which we should be able to do.
Yeah. Yeah, it's amazing. And I'm still going to get back to the telescopes. I'm reminding myself that's a verbal note. But when you're talking about kind of the early, the early astronomers. They're for many societies, and this is not my area of expertise, but they were religious concerns as well. And you read that way before they would have been able to see anything, right? There was the sense in which, or before they would have been able to explain it with the math, they had a sense of what some of these things were and how they, and I always find that just kind of amazing.
Yeah, also, you think about Galileo, right?
Yeah, sure.
He got in big trouble.
Yeah.
But he was he was the standard model at the time.
Oh, right, yeah.
Was not a Christian model.
Yeah,
right?
no.
The whole Ptolemaic system, right?
Right, yeah.
Yeah. So anyway,
there's a lot of. I mean, I guess what I'm thinking about is there was always, and I'm thinking about even pre-Christian societies. I think there was always a lot at stake.
Yes.
Right. I mean, in terms
the
of
Chaldeans and the Babylonians.
Yeah.
I mean, astrology, right?
Right. So it's
We won't talk about it.
No, we won't. We could, but we won't.
But it was very important. But think about that. Kepler was an astrologer.
Yeah.
Kepler took these marvelous observations that Tycho made, and he figured out how the solar system works.
Yeah.
Newton then explained that with gravity.
Yeah.
Einstein then said that's not all there is to gravity, and he did general relativity.
Yeah.
And general relativity begets black holes. So it is a continuum that starts somewhere a long time ago.
And it's funny. I think you can either take it two ways in some sense. Again, speaking as a person of faith, like on the one hand, you could say, how majestic, O Lord, is your creation in all the world. I mean, this idea of the amazingness of it, and the more you learn, and that there are galaxies upon galaxies, and the time and the space involved. I mean, it's miraculous. But the other thing that does is so relativize human existence, right? Sure. And I think for many people that doesn't feel very good, because I think here you are, this teeny little speck on a speck in a speck of the. Wait a minute, right? We're supposed to be more important than that. So I think there are for people still a lot of ramifications about them. What does it mean to be human? But I mean, your point about what an amazing thing that humans are able to do, to be able to build and to study. Right. That's lovely.
Well, thank you. And people ask me, what good is it?
Yeah.
And when congressional staffers ask you, what good is it?
Oh, because of course, they're giving you some money after all.
Money. And you say, it's a gateway science. It brings people into science. We have all this sort of standard verbiage about how many things we get over the fold in the New York Times or the Washington Post.
Oh, over the fold. That's important.
Sort of things.
Yeah.
But in the end, personally, it's like art.
Yeah.
It's good for your soul.
Yeah.
It's good for my soul.
Yeah.
I mean, we've always wanted to understand.
Yeah.
And I don't think it's necessary. I'm not a person of strong faith.
Yeah.
I have had many discussions. I have a very good friend who was the former director of the Vatican Observatory.
Oh, wow.
Who was a Jesuit and writes.
Love those Jesuits.
I love the Jesuits. I love them. They're wonderful.
And even, we could stop for a minute. The Vatican has an observatory, right? I mean, that's sort of a fascinating thing. What's that like? Have you been there?
Absolutely. It's in the Pope's Summer Palace in Castel Gandolfo.
Come on.
And
It's in the Pope's Summer Palace?
I spent like 3 weeks there. It was fabulous. You walked out and you walked into the castle. It was the old Gandolfi family.
Oh.
Oh, it's incredible. There are the 3 volcanic lakes. Nemi, which is where what's his name? Caligula had the big barges built, right? Okay. That were sunk and then restored, and they were destroyed by airstrikes during World War II. But there are these 3 volcanic lakes, and Castel Gandolfo is on the rim of one of these lakes.
Okay.
And it's where Domitian had his villa.
Okay.
Who was a great persecutor.
Oh, of course.
And it's where the Vatican Gardens are, and the Vatican Dairy, and the Vatican Chicken Coop. I mean, you go see the Holy Cow. So we drank milk from
Holy milk,
cows.
really?
Right, really
why not?
but right off the main, in fact, the Pope's summer residence is there. Actually, it's not there all summer.
Yeah, okay.
And then the Vatican Observatory sits on top, and there are actually some telescopes there, and there are some little telescopes out in the Pope's summer gardens, and they're staffed by Jesuit astronomers, all of whom are Jesuits and have PhDs.
Of course,
they have research careers.
Wow. Did the church build it? Did the church pay to build it?
Yeah, the church was interested in timekeeping.
Yeah.
Church was interested in the glories of God.
Yeah, right.
And actually, the Vatican the observatory has a collaboration with the University of Arizona in Tucson.
Oh.
So they will have the Jesuit astronomers in residence in Tucson.
Okay.
And they actually share they have a little telescope. actually a decent-sized telescope, a 72-inch telescope on one of the 10,000 feet on one of the mountains outside of Tucson.
Wow.
So, this trying to understand this.
Yeah.
I must admit, I do not spend much of my time thinking about it.
Okay. You've got enough things to think about.
I was walking. I drove up to your parking lot today, and I looked at this absolutely smashing setting. It's beautiful up here, and I looked at, the wonderful clouds and the spire of your chapel, and I thought how complicated things are.
Yeah.
That we would have a universe that would make such a place with and creatures who can do such things.
Yeah.
That, you can wax that way.
Yes.
When it comes down to it, I'm more interested in, what's going on. Where's all the matter in the universe? What are the outstanding questions?
And are you interested in those questions just for the questions themselves, or they do have larger ramifications for you? Is it part of a larger picture?
For me, I think it's still curiosity.
Okay.
It's there's been such growth in my in my time as in thinking about this before I came over here.
Yeah.
The changes that I've seen in only 40 years.
Is that been because of the what technology in terms of
in
telescope?
Large measure, yes.
Okay, has been made possible.
It's been made possible by that. It's been made possible by adequate, if not abundant, research funding.
Okay.
Which is not just federal, state, private. Astronomy has always benefited much more than physics. We have two things. We have much better pictures.
That is true.
We win.
Yeah.
You can stack. We win the picture competition, right?
Yes, you do.
Because not only do we have pictures of the heavens, we have pictures of these marvelous structures, these telescopes, right?
Yeah.
And so we have always benefited from private funding.
Yeah. Sure.
The Large Synoptic Survey Telescope, which is a new telescope. I mentioned. I don't know if I mentioned it while we were recording. It's being built in Chile.
Mm-hmm.
It's a giant camera, and all it will do is take photographs of the sky, one after the other, after every 15 seconds.
Wow. Okay.
Each one of these, each individual image will allow you to see things 1,000,000 times fainter you can see with your eye. And it will produce many, many terabytes of data a night. It will look for transient things, things that explode, things that move. It will eventually all these data will be overlaid to produce the deepest, widest, all the accessible sky will be revisited every few weeks. It's basically being built to try to understand what the dark energy is, which we could talk about if you wanted to. It's really one of the most outstanding questions right now. But it is...
and you keep saying there's nobody manning or womaning that telescope?
There'll be a staff there.
Okay.
Absolutely. But the
program
it
gets
is programmed.
in? Okay.
But what I wanted to point out was it was funded, the design and development, which NSF supported.
Okay.
They enjoyed $20 million of Bill Gates' private money. Not his foundational money.
Okay.
But
but his own.
And Charles Simonyi, who was another Microsoft, wrote $10 or $20 million check.
Why wouldn't you want to be involved in something
so
like
we've
that?
always had that. The LHC doesn't get private funding.
Yeah.
So
I want to ask you about how telescopes work for a minute, and then we'll come back to dark matter. And I just want to say again that if you're just tuning in with us, this is Kristen Largen here with the Seminary Explorers podcast, and I'm so pleased to be having a fascinating conversation with Dr. Craig Foltz, who is in the physics department down at Gettysburg College and an astrophysicist. And we were just starting to talk about telescopes because, I know so little, I'm not even sure I can formulate my question. So when I think about, you're talking about taking a picture. So I think about holding up my iPhone and taking a picture. But I'm thinking about the distances that are involved here. And so how does a telescope, and even the telescope itself at the magnitudes that you're talking about, how do they work?
Well, first of all, I'm a bit of an optical chauvinist. I tend to think about telescopes as things that live in domes on top of mountains and work it.
Yes.
In colors of light that you can see with your eye, right?
All
or
right.
nearly.
Okay.
And really, that's not the whole story.
Okay. Is it bad that you're an optical chauvinist, or I've never heard anyone called an I don't even know what that means. But if you're one, I think I like them.
I don't care.
Okay.
No, I've used radio telescopes. I've used X-ray telescopes.
Radio telescopes.
Okay.
Oh, I was, of course, just thinking about optical
Telescopes.
Yeah. Okay.
The fundamental, so many fundamental changes have happened. We have radio telescopes on the ground. We don't tend to have them in space yet, but these are spectacular arrays of giant dishes, right?
Okay.
Hundreds of dishes, and
wow. Okay.
in this plateau in Chile, right, at 16,000 feet.
Okay.
Looking at trying to bore through molecular clouds to see star formation in the Milky Way, or see protoplanetary systems forming, see disks of gas and dust forming planets around other stars. I mean, this is spectacular stuff. And it does that by observing light at wavelengths that we can't see. Right?
Okay.
So in the case of the last telescope I described, it's more like microwaves.
Okay.
If you think about light going from radio waves, it's all the same phenomenon. Radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma ray. They're all the same thing.
Okay.
It's just the same. It's just they have different energies.
Okay. Okay.
And when they have an energy in the range that you can detect with your eye, that energy is interpreted by our eye as color.
Okay.
So red photons, red bundles of light, have less energy than blue bundles of light.
Okay.
Okay. So
amazing. Okay.
So the idea of a telescope is collect a whole heck of a lot of that light.
Okay.
As much as you can grab.
Okay.
And figure out some way that you can measure its characteristics.
Okay.
And maybe that's just making an image.
Okay.
In fact, an enormous amount of modern astronomy is done with image. And it could be an image taken in X-rays.
Okay.
So you could look at the Crab Nebula, a supernova rim, and you could take a picture of it with an X-ray telescope called Chandra that's up in space.
Okay.
X-rays don't make it to the ground. That's a good thing.
Oh,
That's
all
a
right.
really good thing.
Okay. What would happen if they did?
Well, they're mutagenic.
Okay.
I mean, they're carcinogenic.
Okay.
I mean, that's why they put the
We
lead.
all look really different.
You go to the dentist to put that lead thing on you.
Okay. Alrighty. So how come they don't make it?
They ionize
Okay.
Air.
Okay.
I won't say exactly which. but
Okay. Good.
Yeah, there's a lot. A lot doesn't make it through. A lot of infrared gets absorbed by water.
Okay.
In the atmosphere. Gamma rays don't make it either, and that's probably a good thing.
So that's why we need telescopes
That's why
in
we go to
space.
space.
Okay.
And it's very expensive to go to space. It's titanically expensive.
I can't even
to go to
imagine.
space.
What kind of telescope is the Hubble telescope?
It's an optical infrared
It
telescope.
is?
Yeah.
Okay.
It's a 100-inch telescope.
Okay.
That means it has a mirror in it that's 100 inches in diameter.
Oh my God.
That's chump change. That's an itty-bitty telescope. You could put that mirror... I mean, you have a lovely office.
Yes.
You could fit the mirror in
I
here.
can fit the mirror in here.
The mirrors that we're talking about for modern telescopes are 30 meters, 42 meters.
Wow.
For the ones that are really, really going after the famous objects.
Okay.
That's not necessarily all you want to do.
Okay.
I mean, there are,
Right.
The newest solar telescope, which will be the biggest one in the world that is currently in construction on Haleakala, is a 4-meter telescope.
Okay. And what's a solar telescope?
Just looks at the sun.
Just looks
Just
at the sun.
Yeah, it's special.
The sun is special.
Well, it's very special. And this telescope is unbelievable. This telescope is so special. It's made to have unbelievable detail, image quality.
Wow.
That if you took a quarter, I'm trying to work this out, and moved to a distance of 100 kilometers, and you pointed this telescope at somebody 100 kilometers away holding
a
up,
quarter,
it could read the date.
Okay.
You don't do that for $29.95.
No, you're not going to get a special on that.
So anyway, you build your telescope. You build it to function. You build it to a specific kind of job. And this is different than it used to be.
Okay.
It used to be we would build these spectacular, wonderful, beautiful machines. Perfect. There's this great book about the Palomar 200-inch, which when I was growing up was like,
the
it was
thing.
the temple.
Yes.
It was called the Perfect Machine.
Wow.
But they were built to do many, many things. And we're still doing that to some extent. But we're also doing sort of purpose-built. We're building the LSST to attack a certain kind of problem. We're building the Daniel K. Inouye Solar Telescope to attack problems of the sun.
Okay.
And
Yeah.
we build ALMA, this large array in Chile, to look at problems of star formation and galaxy formation. So, it's gotten to that point that the field has grown so wide and so rich that you need different tools.
Yeah.
And the tools are expensive.
Tell me about how you know. I mean, one of the things, again, in my, things that came to me in the course of my learning and study, I don't even know how they came to me, but the amazement of being able to see things so far away. And so I think about, but it takes time for all of that light to travel. Tell me about that. How do we know how far away that is? How does that light? So when you say this telescope is taking a picture every 15 seconds, it's taking a picture of everything things that are close, things that are far.
Everything in that direction.
And how do you get the depth on that? How do you
figure that out?
Okay.
No,
you tell me how to figure it out.
Well, maybe you look at the colors. Maybe
you
say that has the typical color of a galaxy at a distance of 5 billion light years.
But how would you even develop a standard for that? How does
generation upon generation?
Okay, of calculations and
of observations. You have building foundation of looking at what nearby galaxies look like and what happens. The universe is expanding.
Okay. Mm-hmm.
I mean, back to the Big Bang.
Okay. We're still in the bang part.
Oh, absolutely.
Okay.
We're accelerating, which is the hardest thing to figure out. The bang is not slowing down.
Okay.
And that was of the last. Actually, it's amazing now. It's almost 20 years, not quite, 18 years or so. The understanding that the expansion of the universe is accelerating. It should not accelerate. It should slow down.
But maybe we're just not to the slowdown point, right? We don't know.
Gravity should slow it down.
Okay.
Because gravity never stops. It drops off as 1 distance squared, but that never goes to zero. And so all the matter in the universe attracting all the other matter should slow down this expansion of the universe.
Okay.
And it's not.
And it's not.
Speeding up. And that's where the dark energy comes from. But anyway, we have many lines of evidence. I would say we are sure, but I'm not going to say that for you.
You can. I don't care. Go ahead.
The Big Bang as a theory.
Yes.
The Big Bang has no viable competitors.
Okay.
That was not true when I got into the business.
Yeah.
And we know that the universe is evolving. We know that it's changing.
Yeah.
We can look back. I mean, think about this. This is pretty straightforward, right? What Edwin Hubble did was he looked out at these extragalactic nebulae, which he understood to be other galaxies like the Milky Way, collections of stars.
He was the first one that realized that?
He and others about that time.
Okay.
In the first quarter of the 20th century.
Okay.
Actually, Immanuel Kant, the philosopher, called them island universes.
Did he really?
Yeah, he did. Now, he had no reason. I mean,
right. That's
but anyway,
interesting. Yeah. Okay.
What Hubble found out is that they were all moving away from us. And at one point you say, "Hey, we're special."
Yeah, right.
We're really special. And what he found was that the speed with which things were moving away was directly proportional to the distance.
Okay.
So if you had something that was, 3.26 million light years away, and I actually chose that very carefully.
Okay.
Nowadays, if we look on average, something at that distance is moving away from us at 70 kilometers a second.
Wow.
Okay?
Okay.
If you go twice that distance, it's moving at 140 kilometers per second.
Okay.
So that number, 70 kilometers per second per 3.26 million light years is actually is what's called a megaparsec. So the number 70 kilometers per second per megaparsec is Hubble's constant.
Oh.
It's our understanding of Hubble's constant.
Okay.
Now think about this. If you go twice as far away.
Okay. And Hubble's constant is what demonstrates this rapid expansion that's continuing.
It is a characterization.
A characterization of it. Okay.
It tells you about how the expansion is going.
Okay.
At least locally.
Okay.
So it's like this. You're standing on the side of a highway and you look a half mile away and there's a car moving 30 miles an hour, which you can measure.
Okay, sure.
You look a mile away. There's a car that's moving 60.
Okay.
miles per hour. A mile and a half, 90. Okay, that's analogous in many ways. It says that those cars are moving at rates of 60 miles per hour per mile.
Okay.
And if you think about that, you say, how long ago was the car that's moving 60 miles an hour here? It was here a minute ago.
Yeah, you could, okay.
How long ago was the one that it was here a minute? They were all here a minute ago.
Okay.
So a linear expansion like that says everything was here once.
Oh, how interesting. Sure.
Now, that puts you in a really special place. Naively, that says we're at some center, but that's not the way it works. Okay, it's because what it is, it's like what it is not things moving out into pre-existing space. It's an expansion of space.
Okay.
So, in the Big Bang, if I take those cars back to when they were here,
okay,
that's like taking all those galaxies and saying, when was a galaxy a megaparsec away? If it moves at 300, or it moves at 70 kilometers per second, how many seconds does it take to move a megaparsec? And you do that calculation.
Okay.
It's actually just
you could do that calculation.
It's easy. It's the reciprocal of the Hubble.
Honestly.
It's all just units.
Okay.
And you find out that it was here 13.7 billion years ago. So all the matter in the universe was here, and all the places in the universe.
But you don't mean here. Literally, we're moving too.
Nah, space is expanding.
There is no here.
All right, the standard way to there's no here. Think about it like rising dough.
Okay.
With raisins in it.
Okay.
That's a lovely analogy, except that.
That's fabulous.
That's a finite universe.
All right.
Now we're not quite there, but if you buy that,
okay,
that space is expanding. So, you take 2 points out in space, and you come back later; they'll be further apart, just because the space is expanding. So that leads you to, you run it back, and it leads you to a time when space was collapsed or small, and the matter was all here, and it was darned hot.
It was hot.
It was
really hot.
Really, really hot. It was so hot that you really couldn't really even distinguish between matter and light. Okay. Everything was fully relativistic.
Okay.
So, and I don't think that's why one said "Let there be light," but it was all. All acted like light. Now you say, okay, prove this to me. Well, what are the ramifications? Well, the ramifications are. The universe was not always the way it is now.
Okay.
I should be able to see that.
All right.
If I look 5 billion light years away, I'm looking back in time 5 billion years.
Okay. Oh, right, because
it took that much time
for the light to get there. Right. Okay.
And you say, okay, well, you tell me that 13.5 billion years ago there was a Big Bang. So if I go and look 13.5 billion light years away, I should see the Big Bang. And you do.
You do.
You do. You see, it doesn't matter.
Can we see that far?
Yeah.
We can.
But it's not. Here's the rub. Okay. First of all, it doesn't matter which direction you look.
Okay.
Because you're just looking back in time.
You're just looking back in. Oh my gosh! My mind is just almost dripping out of my ears, but I'm still with you. It's just amazing.
So we're almost there, right? So when things move away from you, their light gets shifted to longer wavelengths.
Okay.
The energy of the photons decreases.
Okay.
So it's called a red shift.
Okay.
All right. And remember, the further you go away, the faster things seem to be moving.
Okay. Right.
So if you look all the way back to sometime about 100,000 years after the Big Bang, it's moving really fast. It seems to be moving really fast away from us. So those photons, which were emitted at a time when the universe had a temperature of about 3,000 degrees. It had cooled off a lot because it was really, really hot. All right, it's 100,000 years. It cooled off quite
cooled off quite a bit.
About 3,000 degrees.
Okay.
Are now characteristic of a gas at 3 degrees above absolute zero. Very cold. It looks very cold. And so where it emits is in microwaves.
Okay.
So this is called the cosmic microwave background.
Oh my gosh.
It was discovered in Holmdel, New Jersey, using a dish that was meant to communicate with the Telstar satellite. And they had this extra noise in their signal, and they couldn't figure out where this came from. And it didn't matter where they pointed it.
They always
saw this noise. And they went out and they found out that pigeons had taken residence in this horn. And of course, pigeon poop has temperature. And so, it would have been a source of noise. Yeah. So they shoveled it out, and they still had the noise. And what they finally realized, with the help of another astronomer just down the road in Princeton,
oh my gosh,
I think that's right, I may be wrong here, but was that no, they were seeing the remnant of the Big Bang. Now, we can study this remnant. We study this now, and we study it from space with these unbelievably sensitive observatories in space. One's called WMAP.
Okay.
And we look for little structure, because the universe it started out smooth. How did it go from being smooth, just smooth uniform distribution of gas, to being lumpy? The universe now is lumpy.
The universe is lumpy.
It's lumpy.
It's like people.
Yeah,
we're lumpy.
We get
also.
older. Kind of
So the lumpiness sort of thing. Right.
I can deal with it.
It's all right.
So anyway, that's the stuff. We look out and we see the Big Bang. And you can ask, well, what else? Well, you should see changes. You should see the universe should be different, and it is different. If I look at the number of quasars that are around now, there aren't any big ones.
Yeah,
they existed back in time.
Yeah. When I was talking with Dr. Stevenson, your colleague, she had said that's the to talk about a theory, it needs to predictive, or it needs to be able to say, okay, if this is true, you should be able to see these things, and
it does, and it needs to be testable. It needs to be
right.
You need to be able to rule it out.
Yeah,
and you can't rule it out.
Yeah.
Now there are issues. There are serious issues. We don't know how. We don't know how the galaxies formed so fast.
Okay.
We don't know how black holes formed in the early universe. We don't see the first generation of stars. We should be able to soon.
Okay.
We'd like to see, making stars. Look, the universe started out as hydrogen and helium. That was all.
Yeah.
And now we got gold and platinum and stuff, and so that's wonderful. That all happened in stars.
Okay.
Stars do that.
Okay.
But to make a star out of just hydrogen and helium is very hard, because the gas that tries to collapse can't cool.
Okay.
So these are still issues. It's not the structure of the universe, but it's the evolution of the stuff in the universe.
Okay.
There's still
that's interesting.
And there's still a lot of work to be done. Enormous amount of work to be done.
Yeah.
So
that's exciting. Well, we are at time, and I have a million other questions for you. I'm going to hold myself back from asking them, but thank you so much for spending time with us.
It was a pleasure.
You're a delightful teacher, and I just think I can imagine how it would be really important in your field to be engaging and clear, and how easily when you talk about science the way you do, that you could get people excited about
thank
it.
you.
It's just fabulous.
That's very nice to hear.
All righty. Thank you so much.
You have been listening to The Seminary Explores from historic Seminary Ridge in Gettysburg, Pennsylvania, a production of Gettysburg Seminary. We invite you to visit our website at www.ltsg.edu. Opinions expressed on this program are not necessarily those of Gettysburg Seminary or the Evangelical Lutheran Church in America.